No, finish them. So, where was I? Okay, here. You were asked to do these questions yesterday, so whether you copy this down or not, that's up to you. Couple things that I want to point out. I'm going to bring up my formula or my redox reaction table. As I find it. Okay, so when you have the redox reaction table, you need everything present on that side of the reaction to be able to do the for a reaction to take place. Okay, well, that's not going to come up. All right. So here's my redox reaction table, possibly. Okay, here we go. So in this table, if I have PbO2, but I don't have so if I have PbO2 and I have SO4, but there's no hydrogen present in the solution, no hydrogen ions present, that particular reaction will not take place. That particular redox or reduction half reaction will not take place. Because it doesn't have all of the entities. The same thing over here. If you have the chromium 3 and you don't have the water, the reaction going from right to left will not take place. You will not get dichromate out of it. You might find our chromium 3, where are you? Okay. No, because it's only chromium 2 on that side. So chromium 3 won't act as a reducing agent unless it's in the presence of water. Now it's a miserable reducing agent or oxidizing agent because it's way up at the top here. The ones where it comes in that we use a lot, okay, is this one and this one. Well, not that one. This one and this one. Okay. Notice where they are in relationship to water. If I have those two guys and I put them in water and they have everything present, because so if they've got the dichromate and the hydrogen ion, that's your OA, and over here water is right below it, and that's the only thing in the solution. What you have is an immediate spontaneous reaction of the dichromate, acidified dichromate reacting with water. Now, that may be what you want. But if I'm doing an experiment and I'm trying to figure out the concentration of, well, the one we do quite often, concentration of the iron 2 ion, I don't want that reaction to happen. I don't want the water and the dichromate to happen immediately. So what I'll do is I will have my dichromate up here, and in my beaker, I will have iron 2 plus, and I will acidify this. Okay, so now what happens as soon as I drip some of the dichromate into the solution, now I have the dichromate and the hydrogen ion and the iron. So that's the reaction that I want to look for. I don't want the reaction to take place in the burette. Okay, so I have to add it afterwards, or I have to add it where I want the reaction to take place. Because both dichromate and the permanganate that we use for these type of reactions will react spontaneously with water if they have access to that hydrogen ion. So, as I said, in the burette, I'll put the dichromate or the potassium permanganate solution, and in the analyte down below in the burette, or below the burette, I will put the hydrogen ion with whatever I'm trying to analyze. So that's an answer to one of your questions today on the assignment. So here we have just a basic one, 5 steps. First step, write down what you know. So zinc metal, it's the elemental form of zinc. Hydrochloric acid, it's one of our 6 strong acids. What's another strong acid that we have?
Nitric acid.
Nitric acid. Hydroiodic acid, hydrobromic acid, sulfuric acid, and perchloric acid. What's special about, why do we call them strong acids? Because I can have 2 solutions of hydrogen chloride and hydrogen fluoride that are just as dangerous, even though hydrogen fluoride is a weak acid. Strong acids dissociate completely. So those 6 acids that I mentioned, now if you turn to the last page of your data booklet, and you will see the 6 acids at the top of the list. I think it's the last page or second last page. And maybe third last. Oh, right there, where you're open there. So the 6 strong acids are listed at the top of that page. They dissociate completely into hydrogen ions and an anion. Now, if I said acetic acid would be there by itself because it doesn't dissociate completely. Zinc is a reducing agent. Hydrogen ions are an oxidizing agent. And chloride is the chloride ion is a reducing agent. What did I miss? Water. I have a solution, so I always have water. It's an OA, and then it's an RA. Which is the strongest reducing agent? Well, we've got the chloride ion by itself here. We got chloride ion with water there. And down at the bottom, near the bottom, we have zinc. Ashley, which one's stronger? Zinc or the chloride? Zinc. We also have, we have 2 oxidizing agents. We have hydrogen ion there, and we have water down here. Which one's the strongest? There. Hydrogen ion, yes. So now we just get to write out our equation. Now remember, with my reducing agent, I'm writing it from right to left because I have zinc. Got to be on the right hand or the left hand side. Nice thing is that our electrons gained and electrons lost are balanced. There are two, actually, and the last step is we go back to our table and we find that this is a spontaneous reaction. Oh, for Pete's sakes. So going back to how I know it's spontaneous, my oxidizing agent is here, my reducing agent is there. My oxidizing agent falls above my reducing agent on the table. Now, there are three get to the right page. There are two observable quantity or things here, and there is one measurable one that we can do also. What is something that you can observe with your eyes as this reaction takes place? Yes? We have the zinc disappearing. The zinc will have less mass. It reacts. What else can we see? Yes? We have bubbles formed. So those are the two things that can be seen. There's a measurable quantity that can be tested on this also. And it has to do with the concentration of that. Because the hydrogen ion is being used up, its concentration is going down. Is the substance becoming less acidic or more acidic as the concentration of the hydrogen ion goes down? Less acidic or more acidic? Okay, concentration of the hydrogen ion goes down. That's what causes our acidity. So the acidity is going down. The pH level is going to become closer to 7. So you can always, anytime you have hydrogen ions either being created or being reacted, you can always have some type of a pH change. So here we have again the products of a reaction of tin chloride with ammonium dichromate acidified with, okay, well that, I don't like the way this is worded. I would not put the hydrochloric acid in with the ammonium dichromate. I'll put it within the tin. So we still have it though. So I would say acidified tin 2 chloride instead of acidified ammonium dichromate. Just like I said or said earlier, if I acidify the ammonium dichromate, it's going to react with this water in its solution, and that's the first reaction that will take place. So we have tin 2. We have chloride. We have ammonia plus 4. Now the dichromate You could find, if you don't remember what it is, you can find it on the front page in your table of polyatomic ions. Get used to it because we're going to be using a lot of the dichromate. It has access to the hydrogen ion, and because they're all solutions, we have water. Now, a couple things with this. Ammonia does not exist on our table. I'm not sure it doesn't, I'm not saying it doesn't exist in some other redox table, but it does not exist in ours. We've done chloride quite often. It's a very weak reducing agent. We know this guy over here is an OA and an RA. We should be getting into the habit of thinking about hydrogen as an OA. The dichromate, or the acidified dichromate, is here. So we have the dichromate ion plus our hydrogen ions. So that's an oxidizing agent. Now we make a mistake quite often here. Hey, tin 2 is a oxidizing agent, and we leave it at that. However, tin 2 also exists there. So again, that's one of the ones that we need to remember, that exists on both sides. So the tin 2 is both an OA and an RA. The dichromate, when paired with the hydrogen ion, is an OA. Now, looking at our chart, again, I'm going by my chart in my head. The dichromate is the strongest oxidizing agent. We have 3 reducing agents. We have tin 2, we have water, and we have chloride. Tin 2, water, where the heck did the chloride go? Above the water. So we have our tin 2, our water, and our chloride. Which one's the strongest? The tin 2 is the strongest reducing agent. Please check if I've got the charge right on the chromium, if it's a 2+ or a 3+. So you could open your book and look up that for me. Do I have that reaction written down correctly? And I guess I do. And then our tin 2, again, writing it from right to left. As I start with tin 2, I end up with tin 4 and 2 electrons. Chloe, how do I balance the electrons lost and gained in this one? By how much? Okay. I have 6 electrons coming from somewhere. I need to have 3 of the tin 2s giving off each 2 of those each. Okay. Now, again, go back to your data booklet. I have my dichromate up here. I have my tin 2 down there as my reducing agent. That is going to be a spontaneous reaction. Now again, let's take a look at this. We've talked a lot. We've already talked about it twice. What am I going to see happen to the pH as I use up my hydrogen ion? Okay, is it up or down? Because you've done both. Removing the hydrogen ions reduces the strength of the acid. A weak or an acid with less strength is going to have a higher pH. So the pH in this guy will go up. If you turn to the last printed page, I believe that's the one. Yes, it is. There's another observable quantity or observable quality that we can look at here. You notice that the dichromate ion is colored orange or pale orange, depending upon the concentration. So I'm using up the dichromate. What's going to happen to the color of the solution if I'm using up the stuff that's making it orange? If I'm using it up, it's going to become less intense or less orange. So in this case, we would see a less intense orange color. And if we look at chromium 3, it is a green color. We might see a green color. We won't. We might see the solution turning from orange to green because we have the orange being used up and we're creating something that's green. Tin doesn't have a color, so we don't have to worry about it. Neither tin 2 or tin 4. So that idea of absorbable. That was part of that question. We already did it. Oxygen gas is bubbled to an aqueous solution of iron 2 iodide containing excess hydrochloric acid. So here we have walking through, we've got oxygen gas, we've got iron 2, the iodide ion, we've got the hydrochloric acid. Again, it's a strong acid, so it splits apart into H plus and chloride. Now I put it next to the oxygen because I knew what was coming. Okay. If you put it elsewhere, that's fine. Looking at your table, this is an RA. That's an RA. Iron 2, we have to remember that that's one of those ones that has both. We've dealt with the hydrogen ion a couple times, so I'll put my OA there. Now let's look for oxygen on our table. First time it shows up, O2 gas with hydrogen. We have O2 gas down here with hydrogen also. And I do believe, although I never use it, and there's O2 gas with water, all on the oxidizing agent side. So I forgot to put water on here. I would take marks off myself. So which one of those is the strongest oxidizing agent? Okay, so we have, that's the strongest one listed. We've got our hydrogen down here. So the first substance that's going to react is the hydrogen with the oxygen with 4 hydrogens. We have, I've made this mistake in the past, we have the iodide ion, we have the Fe2 plus, and we have the chloride ion, and we also have the water. Which one of those is the strongest oxidizing or reducing agent? The iodide ion. It's lower on the table. So this here is our strongest. This here is our strongest. How many electrons does this particular one have? Can't remember if it's 2 or not, or 4. 4? Thank you. And it gives me 4 water. Okay? And then my iodide, I have 2 iodide ions reacting to give me an I2 solid and 2 electrons. I need to balance off my electrons gained by having 2 of the iodides, or sorry, 4 of the iodides, I should say. And once again, not every reaction I will ever give you is spontaneous, but that one is. Once again, you have a pH change. We're going to be acidified. We're using up the hydrogen ions. Therefore, the substance is getting less acidic. Therefore, the pH is getting closer to 7. And just by looking at the states of matter in this equation, you should be able to tell me the other empirical observable quality that's changing in this one. Yes? Okay, a solid precipitate form. Now in this case, because this, and I don't really expect you to know the color, but you will see a brown precipitate. You know, because you're going to have, I'm forming a solid here. We don't form any gases, so there's no gases being formed. We'd hard to tell because we're already bubbling oxygen into the system. So it's important that you understand, okay, I've got this right. Now what happened? What can I see or what can I measure as this does it? So look at the state changes. Look for solids and gases. Look for solids disappearing, being used up as reactants. Look for gases being formed, and then obviously look for either hydrogen ions being used up, or in some cases, hydrogen ions being created, depending upon which reaction we're talking about. Now, you should have all done those yesterday, so this should be you checking your work. They were all signed to you yesterday. Only 4 questions here.
Yeah.